I'm going to hand over to Tom Cass now, who's very kindly said that he would chair session 2. We are running just a few minutes late, so Tom, I think if Maud does need her full 25 minutes, including 5 minutes for questions, we can perhaps break for coffee at 11:30, but still have 20 minutes and maybe just slightly shorten the lunch break. Okay.
Okay, thank you very much, Jane. So as Jane said, we're moving now to the second session. And the title of the second session is Understanding Clouds of Path and Their Applications. We're going to have 3 speakers, interspersed with a coffee break. And the first speaker is Maud. Maud, are you there? Are you ready to deploy your slides?
Yep.
So, Maud Lemercier is a PhD student, I think, at the University of Warwick and the Alan Turing Institute. And the title of her talk is Inference from Evolving Populations, Agriculture. Maud.
Yeah, thank you, Tom, for the introduction. So yeah, I can confirm that I'm a PhD student in statistics at the University of Warwick and also a visiting researcher at the Alan Turing Institute. Let me just put my, so today I want to talk about some new methodology to perform inference on time-evolving populations, and in particular an application in agriculture. So I want to start by recalling what is a standard supervised learning problem. So in general, it's the task of learning an unknown function, an unknown map that maps input vectors of features to an output of interest. And so there is a wide range of models that is now available to model this unknown function, ranging from simple linear regression models to kernel-based models, or even at the other end of the spectrum, complex neural network architectures. And once you have decided upon a specific model, you then fit your model to training data, which comes in the form of input-output pairs. Now, there are cases in real-world scenarios where you don't have one label per input vector, but rather at the group level. And in machine learning, these kind of problems are called distribution regression. So that's because you can think of the input set of vectors as a sample from an underlying probability distribution. There is a specific example of this kind of problem in astronomy, where, for example, it's particularly difficult to measure the mass of a cluster of galaxies. However, you may be able to observe the velocities of each galaxy in the cluster. And from that, you may be able to infer what is the mass of the global system. So now, in fact, we cannot use standard supervised learning models to tackle this distribution regression task, because standard supervised learning models would expect to always get an input vector which has a fixed dimension, and that's not the case when you have a group of inputs. The cardinality of the group may change from one group to another. A naive approach would be to take the average of the input vectors that you have in your set. But obviously, you will not be able in this way to represent the full information that you have about the probability measure. So more specifically, what we want to do today is to talk about a new methodology to do distribution regression in the case where each input in your set is a time series. So in other words, we want to perform inference on a time evolving population. So for example, we can consider a population of particles and the task of inferring what is the temperature of the gas in which these particles evolve. So in this case, what you would have in input of your model is a group of trajectories in 3D described by the particles that make the gas. As you can see on the picture, when the temperature of the system increases, the complexity of the trajectories increases as well. So this is because under higher temperatures, the energy of the system will increase and the velocities of the particles as well. So they will tend to bump more quickly into each other, into the walls, resulting in these complex dynamics. So as you can imagine, it's a real challenge to represent this kind of data in a vectorial form, such that we can eventually use more standard machine learning techniques to perform inference. And that's the aim of the talk today, is to describe a technique that exactly does this, provides us with a useful, informative representation of this complex group of data streams. So the methodology that we propose is based on kernels. So what comes next is a bit technical, but I hope that I will provide the higher level big picture. So the principle of kernel methods is to discover nonlinear relationships from input data. And how does it work? It works by finding a feature map and mapping the original input data points into a higher dimensional space where where you can then deploy linear regression techniques. So as you can see on the picture, originally in the original input space, the points were not linearly separable, but once you map them into a higher dimensional space, then you may be able to find an hyperplane that separates the points. So that's the general principle. And then the challenge is to find a feature map, a feature transformation of the original data that is expressive enough and has this property that it linearizes the original complex nonlinear problem. So kernel methods rely on the ability to be able to measure the similarity between points in the higher feature space. So in general, the feature map may be quite high dimensional, even possibly infinite dimensional. So you cannot expect to be able to compute it in quickly. And sometimes you may not even be able to compute it. However, kernel methods just rely on the ability to measure similarity in the feature space. And so this is expressed in terms of a dot product in the feature space. And when you have such kernel functions, you actually don't need to materialize and to compute explicitly these embeddings of the points in the higher dimensional space. And that's often called the kernel trick. So now, if we consider the problem of performing inference on data streams, an ideal feature map is the signature. So this is where rough path theory comes in. So the signature has this property that once you compute it, you can just perform simple linear regression on your new representations of the path. However, the dimension of the number of signature features increases quite quickly with the dimension of your input stream. And so in this setting, it's maybe interesting to consider instead the similarity measure that is the signature kernel. And as Terry alluded to previously, there is a kernel trick that makes it possible to evaluate this kernel without explicitly computing the signatures, and that amounts to solving a partial differential equation. And we now have some software that makes it possible to compute in parallel and to solve these multiple PDEs in parallel on GPUs. Okay, so for the distribution regression task, where I recall that we want to perform inference on groups and time series, the first thing that we have to do is to find a manageable representation of the group of time series that we have. And the map that makes it possible to do this is the expected signature. So the signature can represent a single path in a unique way and in a vectorized way. And this expected signature does exactly the same for a group of time series. And in practice, computing the expected signature from a group of time series amounts to just taking the average of your signature vectors. A nice property about the expected signature is that you are ensured that if two distributions are different at the start, and you take their expected signatures, then the vectors that you get are different as well. And so it makes it possible to answer questions such as, are my two distributions of particles different or not? Also, I should say that, so the expected signature is in theory an infinite vector of features. However, you might consider to truncate this vector and only retain the first features. Actually, one justification for doing this is that when you go down into this vector of statistics of your group of paths, the last terms are less and less important. So you might just compute with existing libraries the expected signature and feed it into classical machine learning models, including neural networks. However, what I want to, so the methodology that we propose consists in theory, taking into account the full expected signature. That is, we don't want to truncate it, and we want to learn nonlinear functions on the expected signature without even computing it. And so this materializes as the definition of a new kernel on path distributions, clouds of path, that is expressed in terms of an exponential kernel combined with the expected signature. Now, what matters to us is we only need to be able to compute to evaluate this kernel to solve a practical problem. And it happens that this kernel, this similarity measure, can be computed just in terms of the original signature kernel that we defined before. So that's quite practical. Now, it takes time because you have to measure the similarity between a lot of pairs of input paths, but thanks to the parallelization that I mentioned before, this is now feasible. So I guess now I will move on to the application in agriculture. So there is now more and more machine learning modelers that are trying to predict the crop yields across different regions. And this is made possible because there is more and more data sets that are being made available. Although I should say that it's still, the data is quite scattered around, and it's not always easy to form these data sets. And so now there are some statistical offices that publish regularly yield data, especially in Europe. There is the Eurostat office that every year publishes the yield data for different types of crops across different regions in Europe. So now these data are available at a quite coarse level. So this is what I've tried to represent on the left figure, on the left panel, where you can see the so-called NUTS2 divisions of Europe. So as you can see, it's quite coarse. However, the meteorological data that we may want to leverage to predict the crop yields are often available at a very much finer spatial resolution. So typically around 30 kilometers. This is because now that there are technologies that mix together ground-based sensor measurements and very complex models, and can simulate what is happening at a finer spatial resolutions. And so what I've represented on the right figure is some profiles of the temperature across a region called the Bourgogne in France. And I've focused on a specific week that is ranging from April 25 to May the 5th. So it was during spring 2016. And what happened at this time is that there has been quite a lot of, how do you say, extreme weather conditions. Notably, if you can see between April 27 and April 29th, there has been a frost event, so the temperatures were quite low and below zero, and this has resulted into catastrophic damages for vineyards in this specific region. Also, for the bottom plot, which represents the precipitation rate across the region, there has been haze and storms, and a lot of precipitations, which has triggered and has been followed by higher temperatures. And people say that during this year, this has favored the development of diseases in the crops. So it was a particularly bad year, and we hope that that the signature, in particular the expected signature, could pick up this kind of phenomenon to predict better the crop yields. So I also think that it's a good example to motivate why we want to take into account groups of time series. So I hope that you can see on the figure, which is quite messy, that there are multiple measurements taken over the region, which results in multiple profiles of temperature. And if we were to take the average of this time series, for example, the temperature, maybe that would describe quite well the overall phenomenon. However, for the period where there was the frost in April, in end of April, then we would not be able to pick up this. And this slide actually sums up what I've said before, is that the response of a system, and in particular populations of crops, is not the same under variable conditions that it is under average conditions, which I hope motivates the fact that we don't want to just take the average of the time series, which is nonetheless a technique that most people do to be able to fit these complex multidimensional data streams into classical standard models. And so I'll finish the talk with some preliminary results. So for this experiment, I've gathered yield data across the 22 nuts level 2 regions in France from the Eurostat data sets. So that was between 2015 and 2017, so including the year where there was a lot of damages on the crops and in particular the vineyards. However, here I've taken the yields of the wheat crops. And in terms of weather input data, I've considered the precipitation rate, the temperature, and also the soil moisture at 10 centimeters. So of course it would be interesting to take into account more weather variables. However, it's a bit costly to acquire it from the GLDAS database. So, so what I've done so far. And the results are quite promising. So the baseline in the table consists in only taking a very simple model that computes the average of the yields in the training data and then just predicts this for any new input region. Then I'm considering two distribution regression methods, which is exactly like ours, but does not use the signature kernel, but instead other standard kernels for vectorial data. And so our methods uses the big kernel that I've presented earlier on. and achieves a better mean square error and MAPE. I also want to say that in this setting, I am not taking into account the location of the regions, because this is actually quite a good predictor if you include it, because over a region, the yields may not vary too much from one year to another. But here I wanted to focus on the problem of just using the information contained into the weather time series, so that the experiment is a bit more controlled. And we can see that we are able to explain some the yields outcome. And so I'll just conclude here by saying that future work may involve working more into the interpretability of the models. So it's quite difficult with kernel methods to interpret the function that you have learned. And however, the signature offers very good capabilities to interpret the different nonlinear interactions between the channels that you have in your time series. So for example, it would be very interesting to recover things such as the fact that when you have very high temperatures, you need also to have quite a good amount of precipitation to avoid drought phenomenon. And I think to go further into this direction, it would be interesting to partner with people who are working more in agricultural science. So I'll conclude here. I think I'm on time. Thank you.
Thank you very much, Maud, for a very nice talk. We started a little bit late, so we do have time for some questions. If there are any, I can see the ones appeared in the Q&A. Can you see that, Maud, or shall I read it for you?
No, I can see, thanks. So I read it for multivariate forecast. A good case study is energy demand, many variables, high temporal and spatial resolution. In agriculture, some variables like groundwater, water are difficult to estimate. I think that's not really a question.
That's more of a comment, I would say.
Yeah. So yeah, that's good to hear that that it confirms that it's a good idea to consider high resolutions for the temporal and spatial data. And yes, of course, groundwater is not easy to estimate, but I think that with these new databases like GLDAS, is now possible to get some data. Maybe not everywhere around the world, but yeah.
There's another question. So thank you for the talk. What is the forecasting window? Somebody asks.
So I've used the data ranging from December to March. To June. But I have to admit that I don't so the wheat data, I'm not sure actually if it corresponds to winter wheat or spring wheat. So I was not sure exactly when the harvest month was. So yes, I've just decided to consider the time series until June to predict the final yields.
Are there any further questions? Well, I have sort of a general question about your methodology. You referred to the use of different kernels in different situations. Do you have a sense of what it is that makes one kernel perform better than another in a given circumstance? Is there a criteria that you can apply rather than actually just determining what the performance is on a given set of data? Is there any characteristic of a kernel that you can look at and say that it's, for a given problem, going to outperform another kernel?
Okay, thanks for the question. So from a theoretical point of view, there are kernels which have the so-called universality property. So it means that when you build models with these kernels, you have the assurance that you can approximately well any function, so that is any continuous function and your input data. And then from a more practical point of view, well, there are kernels, there are specific kernels for time series, such as the signature kernel, different kernels for and for general vectors in RD. So depending on what the structure of your data is, you can already select a specific group of kernels that would apply best to this data.
Thank you. There aren't any further questions, and we've now run into the time that's been allocated for the coffee break. So thank you very much, Maud, for that talk. We'll resume in 15 minutes at 11:45, I think, Jane, and then we'll have Thomas's talk, which is the second talk in this session.
That's great. Thanks, Tom. Thanks, Maud.